Okay, let's get started, please. So, somebody tell me what uniform convergence is. Helen? You got a bunch of functions. So, these guys say that they converge uniformly on some set E to a function f. Means what?
It means like the definition of convergence, but for all x in E.
Okay. So can you give that to me a little bit more precisely?
Yeah. So for all epsilon is greater than 0, there exists an n in the naturals, such that for all little n greater than big N, fnx minus fx absolute value is less than epsilon for all x in E.
Okay, perfect. Okay, exactly. Right. So you have some set. You have some set E. You have a function f, and it means that given any epsilon, then there's some time past which all of your functions graphs lie within the epsilon tube here, right? So this thing, the epsilon tube, right? Everybody lies at every point of E, right? At every point of E, your function's values must lie in the epsilon tube of E. Okay, and the Cauchy criterion for that. You just toggle that a little bit, and you say that for all epsilon greater than 0, there exists an n such that for all n and m greater than n, fnx minus fmx is less than epsilon for all x in E. Right. So with the Cauchy criterion, then you don't need to talk about the limit function. Right? You don't know the limit function, but as long as you show that these guys satisfy the Cauchy criterion, well then you're guaranteed a limit function, and these guys will converge to it. Okay. So thinking about the Cauchy criterion, what this is saying is that given any epsilon, there's a time past which, if you take any n past that time. So here's your E, and you take any of the n past that time, and you take an epsilon tube around that guy, then everybody else lies in that epsilon tube, right? So it basically says that there's a time past which each of those functions past that time has the epsilon tube power, right? The epsilon tube property, right? Okay. So, and of course, you're going to know that the thing that you converge to is going to lie in, well, at least maybe the closure of that epsilon tube. It might actually lie on the boundary, right? If you're converging to the boundary, but at least it lies in like the 2 epsilon tube. Okay. Okay. So that just to remind you what we're talking about, right? And we're concerned with uniform convergence because it has a lot of properties that it interacts well with the ideas of calculus, basically. Okay. Okay. So we were talking about Riemann integration. Just to quickly remind you, we defined the upper Riemann integral and the lower Riemann integral over some interval, right? And the upper Riemann integral was the infimum of the upper sums over all partitions, right? Remember that, right? You take your interval. You take partitions, you take the upper sums over those partitions, right? Upper sums over the partitions, remember how it goes, you take the maximum value, and then you take the maximum value over that interval, you multiply by the width of the base, multiplied by the width of the base, and you get this approximation from the top of your area. Right? That was an upper sum. The lower sums are done by taking the minimum over those intervals, right? And taking the infimum over those intervals. And then you take the infimum over all partitions, and that thing is called the upper sum, right? Because as you take finer partitions, these guys are going to become finer approximations from the top of your integral. Okay. And then this thing was the supremum of the lower guys, right? Okay. And so upper and lower sums, right? Upper and lower sums. We also define this thing called a refinement. So if P1 and P2 are partitions, then P1 union P2 is called a refinement. Is called the common refinement. Of this partition, of these two partitions, of P1 and P2. Right? So you take, right, you have one partition, and you have another partition, like that, and then you take all of those points in your new partition, right? All of those points. So P1 here is white, P2 is yellow, and the P1 union P2 is just all these points, right? And so it's it will be the partition that contains all the points of the other guys. Okay. Okay, and I think we stopped last time with this observation that if P star is any refinement of P, then the lower sum just gets bigger, and the upper sum of the refinement gets smaller. Right? I think that's where we stopped. And so we're going to get to the point where we can talk about how uniform convergence and Riemann integration interact with each other. Okay. Okay. So here's our first theorem, that the lower sum is always less than or equal to the upper sum. Okay. In other words, the supremum of the lower sums, the lower integral is always less than or equal to the upper integral. In other words, the supremum over partitions of the lower sums is always less than or equal to the infimum of the upper sums of the partitions. Okay. Okay. So we're going to give a proof by contradiction. Suppose that the supremum of the lower sums actually exceeds the infimum of the upper sums. Okay, so the supremum of the lower sums is strictly bigger than the infimum of the upper sums. Okay, you say, okay, well, in that case, we know that we can find a lower sum, right? We know we can find some lower sum that is close to the supremum, right? And we can find some upper sum that is close to the infimum, right? Because this is the greatest lower bound, right? So we can get close to them, right? So in other words, there exists some P1 and P2 such that partitions of AB such that the lower sum of P1 is strictly bigger than the upper sum of P2. right? This is the least upper bound, and so we can take some epsilon that's half the distance, right? Take some epsilon that's half the distance. We know that we can find some guy above that epsilon, above this minus epsilon, right? Yes? No? Hey, this is the supremum, right? This is the supremum, that's to say the least upper bound, right? Well, remember we have this property of least upper bounds that if you take the least upper bound minus an epsilon, then you know that there's got to be somebody from the set inside there. Okay, so here's our least upper bound, we take our epsilon to be half the distance from here to here, right? We take epsilon to be half this distance, right? So we know that there's got to be some LP1F inside, above here, right? And similarly, we know there's going to be some UP2F that's inside here. Well, then, the LP1F is going to be strictly bigger than the UP2F. So we've seen this multiple times, even on an exam, I think. Okay. Okay, so then let P star be the common refinement of these guys. Okay, take the common refinement of these two guys, right? And you get that well, the lower sum will just get bigger, right? So we get L of P star F is bigger than or equal to L of P1F, right? Which is greater than U of P2F. But if you take a refinement, it just gets smaller, so we get U of P star F. Right? So using the previous observation, right, we get this fact about P star, right? But that's impossible. Why is it impossible? Max?
I was actually going to ask another.
You're going to ask a question, yes?
Yeah, can you explain again why we know observation 3 and why that's true?
Well, think like this, right? If you have a lower sum, an upper sum. Okay, let's stick with the upper sums. Okay, so you've got your upper sums. That says you take the maximum value here, right? You take the maximum value, maximum value, maximum value. Okay. And now we're going to take something that has more. We're going to throw in more points. Okay, so let me just divide. I'm going to throw in one more point, right? I throw in one more point. Well, the maximum value over this part is less than or equal to the maximum value over the whole thing, right? Because the supremum over the smaller guy is less than or equal to the supremum over the larger guy, right? So what's going to happen to this area? Well, it's going to become smaller, right? So you know that as you throw in points, then the upper sum is going to decrease. Okay. Okay. Okay, so now, right, so we get this thing. So we get the lower sum is strictly bigger than the upper sum, right? Which is impossible, of course, right? Right, because the lower sum, is obtained by taking the infimums, right, multiplying the infimums times the widths, and here we got the supremums times the widths. Oh, this is crazy. Okay. So, not possible. Okay, so we know that the lower Riemann sum must be less than or equal to the upper Riemann sum. Okay. Okay, any questions? Any questions? Is everybody okay? You returned. You didn't leave your spirits somewhere. In Taiwan, there's sort of an idea that you might lose your spirit at a particular place, and you have to go collect it and then bring it back. Everybody's here, right? Okay. Okay, so now let's get to the result that was the point of all of this. Suppose you have a bunch of Riemann integrable functions. Okay, suppose you have a bunch of Riemann integrable functions. Okay, and I always abbreviate integrable as integrable. Yeah, to the extent that if you look on my office door, you'll see that this term shows up in the bingo game on my door. So on my door, there's this bingo game that I confiscated from students years ago. Bingo. Right, bingo, with different things that I do in class. Like, did I write integrable as integrable? You know, did I say, okay, let's begin? Did I criticize the TA? Did I disparage the book? Did I glare at this one particular student? You know, et cetera, et cetera. The instructions at the top, right, saying, as Professor O lectures during class, mark down the things that he does. If you manage to get a line or diagonal, then shout out bingo and win the adulation of your peers. Anyway, so anyway, okay. So integrable. Let these guys be Riemann integrable functions, and suppose that you have these guys converging uniformly on AB. Yeah, actually, I didn't confiscate it. They gave it to me afterwards. One of them gave it to me afterwards. After I kept on asking them, what are you guys laughing about? Okay. Okay. So if these guys converge uniformly, then sort of what you want to happen happens. Then F is the thing that they converge to is Riemann integrable. And further, the integral of the limit is the limit of the integrals. So remember, we saw that that doesn't necessarily happen, right? That the limit of the integrals may not, the limit of the integrals may not be the integral of the limit. In fact, although we didn't show this example, there's an example in your book of a bunch of integrable functions whose limit is not integrable. Okay, so even the quality of being Riemann integrable isn't preserved, but if they converge uniformly, then it is preserved. Okay, the limit of integrable functions is still going to be integrable. Okay. So here's the proof. So let for each n, let epsilon sub n be the supremum of over AB of the difference between f and f sub n. This is that distance that we defined earlier, right? This is that distance we defined earlier. Convergence with respect to this distance means uniform is the same thing as uniform convergence. Okay? So we know that this limit is going to be 0, right? Because that's what uniform convergence means. Now this is 0 because that's uniform convergence. Okay, so observe that f lies between f sub n plus epsilon and f sub n minus epsilon. That's also obvious. Right? That's because that's how we made epsilon. So now we take lower sum and lower integral and upper integral of the respective inequalities. Okay, so we get the lower sum of this guy is less than or equal to the lower sum of that guy. Okay, so that's applying the lower sum to the first inequality. We apply the upper sum to the second inequality. Yes?
Can we just do that? Like, can we just take the integral of
Yeah,
this one?
yeah, because it's not hard to see, I guess. You do have to see it that the, if your function is, if this function is bigger than that function, then its upper sums are going to be bigger than, its upper sums are going to be bigger than this guy's upper sums. So the infimum is going to be, the relation will still be preserved. So you have to think about it, but only for like a few seconds. Okay, and by the theorem that we just proved, the contradiction, we know that we have this thing in the middle. Okay, so we apply these guys, and then this is from the previous theorem, Okay, but this thing here, each of these guys was Riemann integrable, right? Each of these guys was Riemann integrable, and certainly the constant epsilon is also Riemann integrable, right? So I know that this thing on the left is going to be the actual Riemann integral of Fn minus epsilon. Right. So this thing on the left here actually is the Riemann integral of Fn minus epsilon, right? Because Fn was Riemann integrable. And over here, we know that this is going to be Fn plus epsilon, the Riemann integral of Fn plus epsilon. Okay. Okay, and then we say, well, look, right, the difference between this and this, the difference, if I take this minus this, that must be greater than this minus this, right? Because these guys are, there's this, right? This minus this is going to be smaller than this, bigger than this minus this, right? Okay. So what do you get? You get that the upper sum minus the lower sum must be less than or equal to the upper guy minus the lower guy, right? This guy minus this guy. But that is just going to be 2b minus a, 2 epsilon times b minus a. And I know this is bigger than or equal to 0 because the upper sum is bigger. Okay, right. And this is true for any epsilon, right? I'm sorry, I should have taken, all these epsilons should have an n on them. Right, from here, all these epsilons, from here onwards, should have an n. Okay, right, and this was true for all epsilon n's, and the limit is 0, right? So let n go to infinity. We get that the lower sum and the upper sum, the difference between them is trapped between 0 and 0. Right? And so they must be equal. Yes?
Can you explain how you get that 2 epsilon b minus a?
Sure, right? Because right, you get this thing minus this thing, right? Well, that's just going to be the integral of fn minus the integral of fn, and the integral of epsilon n minus the integral of epsilon n, right? So what do you end up with? You end up with the integral of 2 epsilon n's, right? Well, that's just going to be 2 times the 2 epsilon n times the width, right? Epsilon n is a constant. So you just pull that back.
Fn got cancelled?
Yeah,
Okay.
right? Because you have a positive guy and you have a negative guy. Yeah, thank you.
So what you showed in the end, is it the limit of, like, is the limit operator before the integration operator or after?
After. I mean, am I taking the limit of, I'm taking the limit of, you mean when I take the n?
Yeah.
I take the limit of n? So these guys are already done. I don't, there's no limit involved here, it's already taken. Are you talking about this, the limits in here, or?
Yeah, like I feel like you should, so like the second claim is the limit as n goes to infinity of integral of fn from a to b. And I feel like that's what this is instead of integral of f from a to b.
Say it one more time, I'm sorry.
So, like, at the end you're saying let n go to infinity, right?
Yeah,
So
right.
if you don't abbreviate, and if you write it out, you will get limit n goes to infinity, the difference between the upper and lower integral of fn. And then I feel like that's not equal to this until you prove the second claim.
There's no fn here though, right? There's no fn, right? This, so, right?
Oh.
This term is
Oh, okay.
between 0 and this. There is no fn.
Okay, so you're not taking the limit of, okay, I see.
Right? The fn's are gone. They vanished. Yeah. So by the squeeze theorem, basically, right? You've got this term. It's trapped between, this thing that goes to 0 and 0. Right? So the term must be 0 itself. Okay. So yeah, there's a second part to this. You say further, since this integral, we know that this guy is Riemann integrable now, right? So we can talk about its Riemann integral, and we know that that's going to be trapped between this and this. Right, so we take the same relation, and we apply the Riemann integral to everything. Now everything is Riemann integrable, so we apply the Riemann integral to everything, and we get this. And you see that the limit of the integrals actually equals the integral of the limit. Okay, so this is good. Any questions? Any questions? Close your eyes for a second. Should I go, who wants me to go faster? Raise a finger. Who wants me to go slower? Raise a finger. Okay, open your eyes, please. I'm going to say the same ways. So there's a corollary, a kind of nice corollary about this. Suppose that Fn are integrable on AB. These guys are integrable on AB, and suppose that their sum converges to some function f uniformly. Right. Then what do you see? The integral of f is then going to be the limit of the integrals of the partial sums, right? From k equals 1 to n, as n goes to infinity. Right? That is the same thing as the limit of the sums of the integrals. Okay. So, I mean, this is sort of the statement and the proof at the same time. I mean, I'm just this. So this is the statement that this equals this. Okay. Notice that what this is saying is that, i.e., the integral of a uniformly convergent infinite sum equals the sum of the integrals. Equals the infinite sum of the integrals. Okay. This is just, what I've written down here is just notation. Okay, this is just notation. This is maybe the more honest statement, and this is the more pretty looking notational statement. Okay, right. So what it's saying is that the integral of an infinite sum is the infinite sum of the integral, which is not true in general. Okay, it's not true in general, but as long as you have uniform convergence, it is true. So this was crucial. And I don't think we showed the counterexample, but there's one in your book to show that if the convergence isn't uniform, then this really fails. Okay. So this is just an immediate application of the previous. Okay. So this is saying that if you have an infinite sum that converges uniformly, then you just need to integrate it term by term. You can integrate it term by term. Okay, yes, Fan?
Just to be clear,
Yes.
this is true for finite series functions?
No, this is an infinite series.
No, just like in general.
Oh, it's absolutely true for any finite series.
Okay.
Yeah.
But
But
then-
if it's an infinite series, then no, not true.
Okay, then can you just like cheat a little and bracket the integral and the summation and then say since this is finite within like the limit operator, I can interchange and then get what I want?
No.
No?
But you really need to use the uniform convergence.
Okay.
Yeah, the uniform convergence is critical. And there's an example showing that it actually is false if you don't have
Why
it.
we use uniform convergence?
Because we're using the previous theorem, right, that said that if you take the integral of the limit, then you get the limit of the integrals of the sequence, of the partial sum sequence, right? So this thing converging to f means that its partial sum sequence converges to f uniformly. Okay, so here's what we're saying, that that we apply the previous theorem. We say the integral of the limit is the limit of the integrals of the partial sum sequence. Okay. But in order to apply the previous theorem, the partial sum sequence had to converge to F uniformly. So it's in this first step that we use the previous theorem.
Okay, so you took the limit operator from inside the integral to the outside.
Yes.
Okay.
Yes. And that wasn't legal. That wasn't legal in general. That isn't legal in general. So the moral is basically that infinite stuff doesn't necessarily behave like finite stuff. But if it's uniform convergence, then it does. Okay, other questions? Okay, so that's uniform convergence and integration. There's no way we're going to get through this. Okay, there's no way we're going to get through this, but we're going to start it anyway. Uniform convergence and differentiation. Uniform convergence and differentiation. So regrettably, even uniform convergence of some sequence to F does not guarantee that Fn prime converges to F prime. Okay, so we had an example at the very beginning, and that example actually converged uniformly. So, previous example, fnx equaling 1 over the square root of n sine nx converges uniformly to 0. This thing converges uniformly to 0, but its derivatives don't converge. The derivatives these guys don't converge. So, right, so the limit of the derivatives doesn't exist, even though the derivative of the limit does exist. So we do have a theorem, but it's not that great a theorem. But let me give it to you anyway. So here it is. Suppose you have a bunch of differentiable functions. Suppose you have a bunch of differentiable functions, and and you know that the derivatives converge uniformly. suppose you know that their derivatives converge uniformly. Not that the functions, right? You sort of hope that it was that sort of result, right? If the functions converge uniformly, then you get something. But in fact, we have to require something much more binding, that the derivatives converge uniformly. And suppose you know that fn x naught converges for some point x naught in AB. Okay, so there's AB, and there's some point where the functions fn converge.
Where x naught is the same point for each, like.
Yeah. So you hold there's this point x naught here, and fn x naught as n goes to infinity converges. Right. Okay. In that case, fn converges uniformly to some differentiable function. And the derivative of that limit equals the limit of the derivatives everywhere. Okay, making sense? Okay, so we get what we want, but we have to kind of put a lot of strong conditions on our situation. Right? We have to require that the derivatives converge uniformly, and that there's this special point. There's a special point where the functions converge at that point. Okay, 5 minutes. I don't know if we can do it. Let's see. So here's the proof. Here's step 1. Maybe we can get through step 1. So let's show that fn actually converge uniformly. Okay, so that's our claim that the fn converge uniformly. Okay. To some f. Okay, so we're going to use the Cauchy, we don't know what f is, so we have to use the Cauchy criterion, right? So we want to show that for all epsilon there exists an n, such that if n and n exceed n, then fn x minus fmx is smaller than epsilon for all x in AB. Okay, so this actually turns out to be pretty easy to show. The point is that we know that that these guys converge at some point x naught, right? There's some point x naught where we have fn x naught minus fm x naught is small, right? We have control over that, and we have control over the uniform convergence. We have control over the convergence of the derivative. Okay. Well, if the derivatives converge uniformly, if you think about the difference of the derivatives, right? The difference of the derivatives we can make as small as we want, right? Because Cauchy criterion, all the derivatives are going to lie in an epsilon tube of each other, right? That tells you that the derivative, we can make the derivative basically 0, right? As close to 0 as we feel like, right? So we know that the functions are close at some point, right? We know the functions are close at some point, and we know that the derivative of the difference is 0, right? So that means that the function is close everywhere, right? That's the idea, right? Okay, so we just basically use the things that we've gotten, or probably the ways that they saw what you needed and then chose these conditions. Okay, so you say, okay, since f and x naught converges, we know that there exists an n such that m and an m exceeding n implies that fn x naught minus fm x naught is smaller than epsilon over 2. Okay. So just use the fact that we have convergence at a point. Those guys are going to be close to each other. Okay. Let's call that n1, sorry, capital N1. Okay. Then, since fn prime converges uniformly, so we know that by the Cauchy criterion there exists an n2 such that if n and m exceed n2, then the derivative of the difference is smaller than epsilon over 2 times the width of the interval. Right, everywhere. And you'll see why we need that b minus a in a second. Right? We know that these guys converge uniformly, so we know that by the Cauchy criterion we can make this difference as small as we want. Okay, then this is just 1 minute. I think we can do it. Then for n and m greater than the max of those, n1 and n2, we see that the distance between fnx and fmx is less than or equal to fn minus fm x minus fn minus fm x naught plus fn minus fm x naught, okay, by the triangle inequality. Okay. As usual, we throw in a 0, right? We throw in a clever-looking 0, right? We take this guy, and then we subtract this thing, and we add it back in, and we pull it out using the triangle inequality. So, right, there's sort of 2 steps done here simultaneously. You subtract, you add, then use the triangle inequality. Okay. But this thing here we know is smaller than epsilon over 2, right? Because we have that convergence, right? And this thing here, right? This is a difference. Well, this is controlled by the the control on the derivative, right? We know that the derivative is smaller than epsilon over 2b minus a, right? Right? Multiplied by the distance between x and x naught. Right? By the mean value theorem. Okay. But of course, x minus x naught is smaller than b minus a, right? And so we get this is less than epsilon. Okay. So what does this give us? This tells us that we do have convergence to some f. Now, next time we need to show that, in fact, the limit of the derivatives equals the derivative of that f. And that will be about the same difficulty. Okay, I'm sorry, I've got, what do you want back? Do you want homeworks or exams? I think you want exams. Exams, and then I'll hand back exams first, and then I'll hand back homeworks.